test. Okay. Well, the first half of the first 2/3 of the recording will be without sound. Sorry about that. Why did this break? That shouldn't break. Also, it doesn't seem to record desktop sound. Or does it? Okay, it records desktop sound. Oops. Okay, let's continue. Okay, so we have our thing, and then we need something to create it. Is equals let's use we need malloc. Size of this plus size of t asterisk times capacity. Okay. So what we are creating is basically an array of pointers to the elements, and the nice thing about this is that it will allow us to access them by index. Although when I think about it, this might not be the... Well, we don't need memory alignment, so let's stick with this design. This is efficient enough, and we can then easily, or at least not too in a not too complicated way, also implement something like an insert function that would insert something into the array at a given offset. And then we only need to copy around pointers, which is more efficient than if we would need to copy around the whole objects. That should be lowercase capacity and return new m. Okay. Then we need something to change the size of this thing. So as mentioned, if we add elements, we will need somehow to expand it. Okay, so if there is no m, then it's really easy. Then we just m is equals create from capacity and return. You're done. And then we check if there is an m, if we actually need to expand, because maybe someone wants to expand it to a lower capacity. So if expand is larger equals the current capacity, then we just return. Nothing to do. And if we want to actually expand, then we can use m is equals copy this, and instead of malloc use realloc, because it maintains the memory content of an already allocated memory block. So if it can expand the memory without reallocation, then it will do it. It will just record in the memory management for the process that now a bigger block is assigned at this address. But if there is already something that was assigned within the range it would need to use, so it cannot expand it without reusing addresses, which would not work, then it allocates somewhere in the address space of the program a new larger block, large enough to accommodate everything, and copies the data over. The important thing to know here is that it really just works bytewise. So if you would have here not just a pointer but some complex type, then it would not invoke the assignment operators or anything, so it would not work properly. So we use just this realloc here, and the last thing we'll need is of course to get rid of the object. So free, call it free. Oops. So obviously if no m, then return for e is equals 0, e is less than m size e plus plus. Okay, and this I will leave as a to do for in a minute. and then we just free the m itself. And then of course last step, m is equals null pointer, just for good measure. And what we also should probably have is a function that allows us to validate if any provided index is valid. So call. That's one of the big advantages of using such container types over normal arrays, in addition to the fact that they can be expanded automatically, is that you can verify indices and prevent invalid memory accesses. Size must be less. Okay, right, so this will be the false case. So if size is less or equals index, then return false, else return true. Okay, now what we will need to add is some append function. So void append const type reference item or value. Okay, so first of all expand whatever we already have. So we need another function, size t get size return. So either m question mark m size or 0. Okay, so expand usize plus 1. And what we could do here is so that if we let's say you have a loop and you're always adding one element, and in each iteration you add one element, that will be somewhat inefficient. So what would be better is if you, for example, would set would like add room for 10 elements, and then expand will be a no operation. So here we could, for example, not make +1, but make like +1 and then multiply the size, or let's take 10% of the existing size in addition, so that you over provision the array at some amount. So you might end up wasting some memory, but you will not waste a lot, and you will increase the performance significantly. Okay, so after we have expanded it, now we can use a trick to increase the performance of our list. So normally, since this is a pointer, we would need to now make a new instance, a full copy, a full deep copy of our t value, and allocate memory for that. And since memory allocations are expensive, and our lists or arrays may often contain, for example, just integers or some other small data type, what we can use is we can misuse the pointer. So if size of t is less or equals size of t asterisk, so basically if the data type is as big as a pointer or even smaller, then we will not allocate new memory, but instead we will use the memory that is already allocated for the pointer to hold the actual data. We can use the new operator and provide to it an address. So reference on the m was it data, p data? It should not be called p data. Let's call it just data, because it's an array, it's not a pointer. It's an array of pointers, but well. And here we do m usize plus. So we kind of take the old usize as the index, which basically is the first element after the elements that are already there, and plus increments it after we already got the value, so size will be adjusted properly. And then we specify the type, and then we specify the we tell it to use the copy constructor, so we specify the value. And this is our special case. And the regular case is the else case, where we just data, again at the same offset, is equals new t value. And in this case, new actually allocates some new memory, while here it takes the memory we already gave it, which already is allocated. And now that we have done this, we can go back to our release function and free function and implement it correctly. So and then we can copy already this comparison from here. So if this is the case, then what we basically want to do is we want data at e, take the address of that, take the address of that, then we cast the thing on t asterisk, and then we can use the arrow operator to call a function on it, and in this case we use the destructor. And at this point, if the object was something complex, like for example our CX string, its destructor will be invoked, and the object and the internal data will be released. So this is already done. And of course the else case, there we just delete data at e, and of course once we free it, everything will be gone. So this is a quite efficient implementation. It is missing many things. So we don't have an insert, we don't have a let's write it quickly down what all things are we missing. So append, prepend so basically like insert at 0, then of course insert to insert that takes value and index. I'm not sure if it's not more common to have the index as first argument, but it doesn't matter. It's we can define our functions however we want it. Then we would like, of course, to have a remove function to remove size t index, size t count by default is 1. So by default we want to remove only one element at the index, but we might want to remove more, so we make a more flexible function. Then we will want to have something to get a value at a given index, which we should implement now. We have still time left, and without it the whole thing will be mostly useless. So const t reference at size t index, const, we will implement the whole thing twice, once as const, once as non-const. So if exclamation mark test index of index. So if this is not the case, then we somehow need to get out of here. And the problem is, since we are returning a reference, we kind of cannot, because we need to return something valid. So one thing we could do would be to define like a dummy element which is always which always exists, and return it. But this would be a bit error prone, because if you return such an element, then something might think that it can do something with it, and then you might introduce some error further down the line which you won't catch. So the typical approach here in such situations is to throw an exception. Use the throw keyword for it, and we can throw any valid C type. So we can actually throw a const char asterisk, which just says invalid index. In more professional implementations, you would of course not just throw a string, but you would define an own exception class, which contains probably an error code and an error message and whatever else you want, and then throw that. But here, since we want to save time, we just throw a string, and that's it. And then of course our special cases, return, and you can copy, where is it, that much. Index. The other case is just return data at index without anything else. Then we can make a copy of that for the non-const case, so that we return references which can be changed. One thing that could be done here is that we could not return an actual reference, but actually a copy, which is less efficient. But by doing so, we could here, instead of throwing, just return t. But this, of course, is contingent on the type we're using having a default constructor, which is not always guaranteed. So let's just stick to this. Then, of course, if we want to use the square bracket operator, we could just implement it and just call add. So that's quite easy. So we can add here. Okay, so we have type. We can have it with operator. We have size. So this would already be the bare minimum that's needed for it to work. Then we could have, of course, some convenience functions like first, last, take first, take last, which basically is just a combination of taking the first or last element and then removing it and returning a full copy, which often is quite convenient. We might, like for a string, want to have not substring, but we will call it mid, like from the middle, as well as left and right, which just can be defined as special cases of using mid with the right parameters. And of course, what also would be nice at some point would be some sort of find function, but how we implement find, that we would have to decide, because we could either use it in a simple way that we just say, okay, you specify something of type t and then it has to find that thing, and that thing needs to have a comparison operator. Or one could implement a much more sophisticated version of find, where our find would take a function which actually does the comparison. So you give it a function pointer, and that function is then responsible for comparing. So that might be something we would want to add later on as well. Find. And one thing I might be able to do in the last 10 minutes is to implement an iterator type. So stoked as so that we will be able to use ranged loops like this one with our own array. So we have the iterator. What will that thing need? It will need a pointer to our... Okay, then this thing needs to go up. So we will want to be able to access that. Right, let's just make this private. No. Let's keep it protected. We want the iterator to be able to access those things. Okay, so we have our iterator. That thing should have a protected constructor with a friend class, so that our C array can access it. So the iterator will have a few internal mechanisms which we don't want to expose to the outside world, so to say. We need a... I think we need a empty constructor which doesn't do anything. We don't need a destructor, and yeah, what will it need? It will need to access. It should have a copy of m. M. And since it's a array, then it will need to have an index. Index. I mean, we could simplify. It needs the whole m. That will stay as this. Let's let's just call the index I. Let's stick with this. Okay. What else do we need? Then we will need a it will need an assignment operator, definitely, since we are often assigning indices, and then copy constructor. Const reference. Oops. Const iterat. What is the name? S iterator. Reference author. Then reference is equals and here we just make asterisk this is equals other, so that we just use the assignment operator. It is one function called extra, but it saves things. So m is equals author m and index. I don't like the name m. Let's call it array. Array. Okay, so we just assign those two. Nothing special here. Okay, so what we then need will be a operator to increment our iterator. So plus plus, and the thing basically just will increment our index, since this is quite simple. Okay, and then with the same thing again, just so the plus plus with reference is the plus plus something. I forgot to return. So this operator is, I think, if I recall correctly, the plus plus I, and this one without the reference is the I plus plus. Technically we only need this one, the other one we don't need. This is the same, but it returns that will be the funny thing. It needs to make a copy of itself. Alt is equals asterisk this, and it returns the old copy. Okay, then we will need something to compare iterators. Pol Operator ungleich not equals other. And here we just check turn array is equals is unequals array, or index is not equals index. The other indexes needs to be from other, of course. That was with a dot. And here it should be with a dot as well. And this is array. We renamed it. Right, we usually don't do the positive comparison, but let's add this operator as well. Let's make that we could kind of just use the one for the other and then just inverse the result, but since this is a really simple one, let's do it this way. And then we will need something to access the contents. So t asterisk arrow turn reference array array.data at index. Yet one more operator, the reference operator, which just is this. Almost right. We have only 3 minutes left. I have to be quick. Then we are only missing a constructor here to make this constructor which will take an array and an index. And since we use the same names as arguments and in the object, we can use this syntax to make it work. It's because it knows that here that this array cannot be that array because it wasn't yet initialized, while this one obviously is supposed to be something that is defined here to be initialized. So this syntax works. If I would use it here inside the body, then you would need to use different names because at this point they would become ambiguous and it would just take this array every time. Right, so here we have our iterator and then we need a begin and an end function to get them. And now it must be non-capitalized, it must be the right begin because the range loops expect this syntax. So return as iterator e m and we can make by default that this is 0. And for end we will use m and basically we just specify a starting index which is already at the end, so we will use size. Wait, size or 1 minus size? No, end is not longer valid, so size, yeah. Okay. And that might just work. Let's try it out. Main array, and let's comment this out. Let's copy this part, and instead of vector it's our, and this is my vect now. CX, my vect, and we don't have pushback, we have append with a capital A. Oops. From int, and here my vect. Okay, we missed something. It wants an asterisk operator. Oh right, this. Wait. It should be the asterisk operator, not the end operator. Okay, it's no longer complaining. Okay, it's okay, a semicolon here. To specify by how much we increment this operator type int e. Size t rather. So this will be plus equals I. Okay. Is it though? I put a breakpoint here, I'm not sure because I think the int is just a formal parameter. Must be int, okay, then int. Reference data. Oh, we always complicates things in both cases actually, because we have our special case. Let's do it differently. We will give to the iterator this. I don't want to implement like this special case specializations everywhere, so let's see. We assign things, and here we will just use array at index. We want a reference on that, and here we will just use array at index. Okay, this way we don't need to handle these special cases again and again and again. And other than that, that should be fine. Yeah, here almost fine. Something's broken at our add. Okay, we are already over time, but I think if you don't mind, we can spend a few minutes to make it work. So we take the address from the thing. We need to dereference that thing. And here it's a pointer, so we need to do the same thing. It's an array of pointers. Yay, and it works. Very nice. I think here, where is it? I think here we are not using this case at all. But I think the right thing to do is plus plus, not plus I. Okay, so as you see, this works, and this allows us to use already some of this functionality. We could actually check if reverse would work, or if we are missing some interface for that, because it just might work. It's working on it doesn't. Why? Okay, we would be needing quite a few more implementations, so that will not be for today. Okay, and right. So the homework from today will be our list to implement such an iterator mechanism, which is not very difficult, as long as you're just increasing one or the other direction. So what's the date? 28, 11, 20, 24. What's the name? As iterator. CX list. CX array. Okay, that's that. Any questions? One person already had to leave. Yes? Okay, then again, I'm sorry for the 7 minutes overtime, but it sometimes takes longer. I will upload the recording to YouTube and the project to Moodle, and we'll see each other for the lecture in 3.5 hours. See you. Bye bye.